I think we left off towards the end here. So let's talk about sort of free-falling bodies. So if you throw an object up into the air, that's the same as last time, Eddie, because I think you've already got it. If we throw an object up in the air or we drop something, then it's subject only to the acceleration due to gravity. That's the only net force that's acting on it. We're neglecting, obviously, like air resistance and stuff like that. But right, so let's suppose that I throw a stone directly upward, and I throw it upward from a height of 4 feet with an initial velocity of 30 feet per second. Okay, so we throw a stone upwards with initial velocity 30 feet per second and initial height 4 feet. Okay, so the first step is we need to write down what the IVP is for this situation. Well, the initial height and the initial velocity tell me that tell me these two things, that S of 0 is 4. We throw it from 4 feet off the ground. That makes sense. It's throwing it out from out in front of you. And the initial velocity, 30 feet per second. Okay, whatever it is. Right. Okay, so those are our two initial values. And then what is the differential equation that governs this? Do we know anything about the velocity or the position other than at time 0? Just 1 second. No. Question?
So is it like the first derivative is the velocity or the speed is the first derivative?
First derivative is velocity. Okay, so S of 0, what does S stand for? Position, not speed. Okay, and while we're on the subject, actually, what's the difference between speed and velocity? Yeah, velocity has a direction and a magnitude. Speed is just the magnitude. Okay, so in our case, the initial velocity being 30 feet per second, that is both a number and has a direction attached to it. What's the direction? Up, meaning plus, right? So for our purposes, for most of the problems, um, there are only two possible directions, up and down, or if we, kind of redrew things left or right or something. So the velocity is a number, but it has a plus or a minus, and that's the direction. Okay. If you want to do physics properly, of course, then you have multiple variables and things get a little messier. But yeah. Okay. And I know this is annoying, but S is the abbreviation for position, not P or something. Sorry, didn't make that up. Okay, but the differential equation in control here is once the thing leaves my hand, what is true? What forces are acting on it? Only gravity. Okay. Now, do we know the mass of the object? No. So we don't know what the forces are, but we do know what the acceleration is. What is the acceleration due to gravity? Okay, and that's in imperial units, negative 9.8 meters per second squared, or in imperial units, it's negative 32 feet per square second. Okay, so I know that the acceleration here, once the thing leaves my hand, is a constant at negative 32. Okay, and that's because that's what gravity is. Okay, so what I need to do to solve this is, well, okay, I wrote the things in this order because what's the derivative of S? V. What's the derivative of V? A. So I want to find the position and the velocity of this thing at various times. So, but I am starting with the acceleration, so I need to find some anti-derivatives to kind of go up the chain. Okay, so um, so that's what we want to kind of figure out. Okay, so a couple of sort of sub questions that we could ask would be, how high does the stone get at its maximum? And also, let's say that I throw it in the air and it's going directly vertically, and eventually it's going to come back down and fall. Well, let's say I'm stupid and I stand in the way and it hits me in the head. How fast is it going when it hits me in the head? Okay. Yeah. So that is just on Earth. That's what gravity is in imperial units, right? So some physicists measured it. Um, Interestingly enough, actually, up in the physics lab, like maybe 100 or so years ago, uh, somebody was doing a survey of uh, the country and finding the exact value of G at various locations around the country. And so we have the Wabash specific value of gravity, as 9.80 and then a whole bunch of extra digits of precision. Um, and yeah, so that's the official Wabash College value of gravity. Okay. Um, yeah, so negative 32 feet per second is or squared is the imperial unit version. And it's assuming, I think, what, sea level on Earth kind of thing. If we did this on the moon, obviously, then the value would be lower. So, okay. Um, so what I need to get to velocity is that v of t is going to be an antiderivative of the acceleration. Well, what is the acceleration? It's a constant. So what functions have a constant as their derivative? 1 degree up. Okay, so linear functions. And so it's going to be, the velocity would be negative 32t plus some unknown constant, and I'm going to call this unknown constant v naught, v sub 0. Okay, and what is the meaning of v sub 0 here? It's the constant that we have to have whenever we find an antiderivative. Okay, but I picked v naught as the way to represent it for a good reason, because what is it numerically here? 30. Okay, now how do I know that? If I plug t equals 0 into this function, what do I get? Well, the v sub 0, right? What was the initial velocity at time 0? 30. Okay, so that's how I know that v naught is 30. Okay, now that we know the velocity, how can we get the position? One more antiderivative. Okay, so what am I doing here to get the antiderivatives of these things? Well, I'm doing the power rule in reverse, right? And we talked about the socks and shoes thing last time. So, um, okay, what is S0? 4, because I throw it from 4 feet in the air. Okay, so S of t is negative 16t squared plus 30t plus 4. Okay, so now we have solved our differential equation. Okay, and that gives us the position. Okay, so now that we have this, any questions on how we got here? Right, it was just basically doing antiderivatives plus using the initial conditions that we were given. Yeah. Mm-hmm. Okay, over 2, not over 2t. What function has negative 32 as its t as its derivative? Well, if I did 32t squared, what would the derivative of that be?
2 times 2 is t.
Right, and so that's why I put the 1/2 out front to cancel with that extra 2, right? So do you accept that the derivative of this function is that one,
Oh,
right? So I'm doing it in reverse, right? Yeah, just to keep everybody on their toes. Okay. All right, so good with the antiderivatives? That takes some practice, and we'll obviously look more at that later. Um, okay, good. All right, so now that I've got the position and the velocity equations, I want to answer a couple of sort of interesting questions. How high does the stone reach? Right, so I throw this thing up in the air, it's going to hit some maximum height before it turns around and starts falling back down. What is that height? Well, I don't know, but how could we find it? Well, if I do that, I'll get 4. Oh, and actually, no, I can't do that because I would get wherever the stone is after 4 seconds. No, not necessarily. So, okay, so let's be careful here. The 4 that's in here is the height at which I throw it. If I plug 4 in, what I'm saying is what happens at 4 seconds, right? 4 seconds and 4 feet are not the same thing, okay? So the problem is, do I know what time the object hits that maximum height? No clue, right? I need to find that value in order to do anything, okay? But let's think then, how could we maybe find that? What's true at the moment the thing hits the peak? Its velocity is 0, okay? And that makes sense, right? Because what's the velocity when the thing just leaves my hand and is going up? The instant it leaves my hand, it was 30 feet per second. But what's going to happen as it goes upwards? It's going to slow down. Okay, so the velocities are positive, 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 but decreasing, and then they hit 0, and then now they turn around and it's negative as it's on its way down. Okay, so the instant at the very top of the path is the moment where the velocity is 0. Well, do we know what the velocity is at any time? Yeah. So could we set this equal to 0 and solve for t? Okay, so let's do that. Okay, so we're going to ask here, when is v of t equal to 0? Okay, and so what do we get? 30 over 32, which if we simplify this a little bit, what do we get? 15/16. Okay, whatever. And what's the unit here? It's a time, so the unit should be seconds. Oops, what's going on there? Who's texting you at 8:17 in the morning?
well, he's the one. He's coming here like next year.
Ah, so it's not 8:17 in the morning for him.
Yeah, it's 7 a.m. 7 p.m.
Okay,
He's moving.
great. Look forward to meeting him. Um, okay, so it's just shy of 1 second that it takes to get to the peak. Um, yeah, okay. Does that seem reasonable? All right, so have we answered the question yet as to how high is it get? No, we just know what time it hits that point. So what do I need to do with this 15 over 16? Plug it into my position function, s of t. Okay, so max height, and I don't know why this is doing this. okay, is whatever we get if we plug that into our function. And just for sake of demonstration, let me just crunch the number here with Mathematica. Okay, so what did we get? It was negative 16t squared plus 30t plus 4. And I want to compute, which comes out to approximately 18.06 to, well, 18 feet, roughly. Okay, does that seem reasonable? Yeah, roughly. Okay. But how did I get that? All I did was I plugged 15 over 16 into here and then just had it crunch the arithmetic for me. Okay, good. So what's the other question we need to answer here? What would happen if we were stupid and stood in the way and the stone is on its way back down and hits us in the head? Let's suppose that we're 6 feet tall, just for sake of a number. How fast is the thing going when it hits us? Okay, well, what do we have to identify first? When it hits us. And then we can figure out the velocity. Okay, so when does it hit us? I know, I don't know what is it. The problem is not the projector, it's this thing. I think I need to replace one of these HDMI cables. No, it's not the projectors. So if he was having trouble last week, I think we got that situation worked out. No, this is all my equipment. That's because nobody else is using this stuff. Um, so um, yeah. Okay. So the stone hits us when S of t equals 6. So we want to know at what time is the height equal to 6 meters or feet, excuse me. I'm not 6 meters tall. Okay, so what do I need to do there? Well, I need to just solve this equation for 6. Okay, and obviously I could pop that thing over, right, and say when is this thing equal to 0? Okay, just to do some simplification. Okay, so let me just have the computer do this real quick. Um, okay, and I get two values here. Why does it make sense that I'm going to get two values? Because there's a squared, okay, so that's sort of the algebraic reason. What's the common sense reason? It's got to go up to come down, right? So it goes through 6 feet on the way up, also on the way down, okay? And so which answer do we want? The one corresponding to when it's on its way back down, which is going to be a later value of t. Okay, it won't be negative because t equals 0 is when we throw the thing. Okay, so we just want the bigger of the two t values. All right, and so with Mathematica, I get these two values. Okay, 0.069 and 1.85. Okay, so clearly which one is the one that we want? The second one, because that's going to correspond to when it's coming back down rather than when it's going up. Okay, so we want this one and we want to exclude that one. Okay, it's not the root we were looking for. Yeah? Okay. The first one is when it's 6 feet going up, right? Which, I mean, it's true. It does hit 6 feet on the way up because, well, it's not teleporting. But that's not the one that's hitting us in the top of the head. So we're just going to throw that value out. Okay. So that's the time at which it hits us in the head. But what were we interested in? How fast it was going. And so what do I need to do with this t value? I need to plug that into my velocity value. Okay, so let me just do that real quick. Okay, and I get negative 27.7849, and then this would be feet per second, of course. Okay, and then let's think about that value to make sure that it sort of is reasonable. Yeah.
So like 32t is the acceleration, minus 32t is the acceleration.
No, just negative 32.
Negative 32, but then what does like minus 16t squared stand for? What is it?
Oh, so the
I know it's like, I know like 32t is the derivative of that one, but like, what does minus 16t squared stand for?
okay, so by itself, nothing. But maybe to some extent we could say it's the term that it isn't the acceleration, but it comes from the acceleration, right? Because what would happen if I took this function and I took its second derivative? What would I get? This term would disappear and that term would disappear. What's the second derivative of minus 16t squared? Minus 32. The first derivative is minus 32t. Right?
So the first derivative is the acceleration?
No, the second derivative of position is. What's the first derivative of this?
It's minus 32t.
Right. So what's the derivative of that?
Minus 32.
Which is the acceleration due to gravity, which is constant because gravity is, I mean, for small bodies that are not like in orbit of the planet and that sort of thing, you can treat the gravity as being a constant. Okay, it's not really a constant, but for small scale problems, that's good enough. Yeah, okay, does that make sense? Okay, so this negative 27, does that number seem reasonable? Okay, now let's compare. Why is it not negative 30? Huh? Say that again, I couldn't hear you. Yeah, we launched it from 4 feet at 30 feet per second. So on the way back down, let's say that we weren't standing in the way. When it passes 4 feet again, how fast is it going to be going? Negative 30 feet per second on the way down, right? And that makes sense because if its velocity is one thing on the way up, it's going to be the exact opposite at the same height on the way down, okay? And the reason for that is physics, right?
So if you plug in 0.069, would you get positive 27?
Yeah, actually, that's true. Okay, so yeah, so Mark's point is what was the other value where the thing was 6 feet off the ground? That just 0.06 seconds. If I plugged that into my position, or sorry, my velocity function, what would I get? I don't have to plug it in to know. I would get just the positive version of this because it's at 6 feet, but going up rather than coming down. Okay, and what's the difference between up and down in terms of our velocities for a single direction thing, plus versus minus? Okay, yeah, does that make sense? Okay, so yeah, so physics is fun, yo. Okay, so all of these sorts of problems start with knowledge about the derivative, the second derivative, okay, or knowledge about the position or the velocity, and then how are they related to one another? What's the derivative of position? Velocity. What's the derivative of velocity? Acceleration. Okay. Now, a couple things here when you guys do this on assessments. So we'll have our first or our next one on Monday, by the way. We're all on the same page there. What do you have to be very careful about when you get crunch numbers here? There's two things. Make sure that you've got the sign correct, right? Because minus versus plus does matter. And also the units, okay? Be very careful to have the correct unit, okay? Now, feet versus meters, okay, that doesn't, I mean, yeah, that matters, but what I more mean is your unit a unit of distance? Is it a unit of velocity? Is it a unit of time? Is it a unit of acceleration? Whatever, right? So think carefully about your units, and that actually can help you keep from making mistakes. Okay. Now, on that subject, in Edfinity, on the problems, you usually will not actually type the units. One of two things is usually the case. They'll be written there next to the box for you, or sometimes they have one of those little drop down things where you have to pick whatever the correct units are. And that's just to keep you from having to type it, because there's lots of ways you could type it. Okay, but just be careful. Think about your units. Okay. Okay, good. All right, so the next thing we're going to start is kind of at first, it's a blast from the past. So let me go get the new sheet from the copier, and then we'll get to it. Hi, Jill. Okay, so come grab one of these, s'il vous plaît. And what we're going to start talking about today, and then we'll continue with this on Monday, are what are called related rates. Okay, so it's sort of apropos given what we've already got. So the essential idea behind related rates is, well, a couple of things. In the previous problem we worked out, position, velocity, acceleration, all of those things, we could give them explicitly as functions of t, explicitly. But there are situations where we can't, okay, and we have to kind of work implicitly, thinking everything is a function of t. All right, so in the same way that you guys remember, this is a couple weeks ago when we did implicit differentiation, and we said everything depended on x or whatever, and then sometimes we had to do the chain rule and we'd have dy dx's popping out. It's going to be the same thing here, except now we'll just say all variables, period, depend on t. Okay? All right, so let's take the following kind of problem as sort of a motivating one. So let's suppose that I have a snowball, and it starts as with a radius of 20 centimeters, okay? And it's going to start melting at 3 centimeters per second, okay? So it's melting. What's therefore happening to its volume? It's decreasing, okay? Could we understand how fast it's decreasing? Well, yeah, that's the object of calculus, right? Now, let's think, is its volume decreasing faster or slower when the snowball is really big versus when it's really small? That's not quite so easy of a question now, is it? And what do you think? Yeah, probably faster when it's bigger. Okay, but we'll find out. Okay. Okay. So if I want to understand here something about the volume of this snowball, okay, I'm going to assume obviously that the snowball is a perfect sphere, What is the volume formula for a sphere? Mm-hmm. And you guys all remember these formulas from high school? Mm-hmm. Yeah, well, I don't know, maybe we should have like a unit circle and basic geometry formulas punishment quiz. Yeah, what do you guys think? Yeah?
Even in SAT, they use like coupling at the top key section.
Hmm?
Even in SAT, they just give us all the formula.
Yeah, well that's the SAT gives you all the formulas? Is this the SAT? No.
This is what we can remember. It's like, you see it.
Yeah, well, you punks. You got to know what the damn volume of a sphere is. Come on. All right. Okay, blame maybe not, but I can tell you that that's not going to fly here. Too late? What do you mean too late? Only have 2 more weeks of school? Try 5, plus a week for finals. Okay. So, okay, are you in a Spanish class right now? You were? Okay, so no more vocabulary because there's only 5 weeks left in the semester, right? Is that what you're saying? That's a big steaming pile of grade A Texas, West Texas Longhorn bullshit. Okay. Oh, no more grammar. You no. I would be happy to print you a transfer application to the university that's south of here, the alleged university. If you want a place where the math classes give you the volume formulas and yeah, I don't know. Yeah. All right. So what I want to do then is I want to understand how fast is the velocity changing. Okay. So v, the velocity depends on t, and so does r. All right. So if I take the derivative of both sides of this equation, so let me write it like this. Okay, so remember, what does the d over dt mean? Or d over dx or d over d whatever? It means take the derivative of that thing. Okay, so it's instruction to do it. All right, so what is the derivative of volume? I don't know. Let's call it dv dt. Okay, now what were you maybe tempted to write there? V prime? Okay, so you could, I would avoid that because the problem with the prime is it suppresses who's the variable here? T, okay? Not R. I mean, R is a variable, but it's not the independent variable, okay? So in situations like this, avoid the prime notation because it'll actually make your life more miserable later, okay? All right, now that was easy. What about the right hand side? What's the derivative of 4/3 pi r cubed? 4 pi r squared times something. But what is r? R is a function. What does it depend on? So we have to multiply by dr dt. This is the chain rule. Okay, so you guys remember when we did implicit differentiation and we took like what's the derivative of y squared and we said it's 2y dy dx or whatever? Okay, same thing except it's now all of our functions are going to depend on t because for time, and all of the functions, well, basically any letter is going to be a function. Okay, we just don't have formulas for them. Okay, so does that make sense? Okay, so this kind of makes sense then logically, because what it says is that the rate at which the velocity is changing depends on two things: the radius and how fast the radius is changing. Okay, now let's go back to kind of a few minutes ago when we just imagined we had a big snowball and a little snowball. Which one was losing volume faster? Well, you guys thought it was the bigger one, okay? But you could have said, no, Dr. McKinney, they're going to be the same, right? That would have been an answer. Okay, is it a correct answer? Well, okay, but we do know that. We do know that the rates aren't the same because the rate depends on both the radius and the rate at which the radius is changing. If there was no r in this expression, then the rate would be the same for the big and the little snowballs. Okay, but the fact that this is there actually allows us to answer the question correctly. Okay, where is it going to be bigger when, okay, so what's drdt? What was that given to be? 3, and it's actually -3 because it's shrinking, okay? But that's a constant, right? So given that, when is this quantity going to be more negative? When the r is a bigger value or a smaller value? Bigger, okay? So what did you guys think? Big snowball going to be losing volume faster or little snowball? And this demonstrates why. Because which one has a bigger value for pi r squared, the big snowball or the little one? The big one, right? Okay, so y'all were correct. The big snowball is losing it faster than the little snowball. Okay, so does that make sense? Maybe like intuitively it made sense to you guys. Yeah? Okay, now that is a generic equation. What we're interested in is how fast is the volume of this thing changing when the radius is 20 and the radius is shrinking at 3 centimeters a second. Okay, so what am I going to do with my 20 and my, well, -3? I need to plug those in here. Okay, but why didn't I plug those in from the beginning? I would give me the volume, but then what do I care about the volume here? No, what I care about are the rates. Okay, so if I plug in the numbers too soon and then I take a derivative, what's going to happen? What? Well, I'll get the wrong answer, but what happens when you take the derivative of numbers? You always get 0. Well, that's not very interesting, is it? Okay, so don't start plugging stuff in, specific numbers, until after you've done the derivative step, because otherwise, if you pizza when you should have French fried, you're going to have a bad time. Okay, I have explained that one to you guys, right? The pizza and French fry. Okay, just making sure. Okay, so what do we have? So dv/dt, you guys remember the vertical bar as a piece of notation? This is one of the places where it's really nice. Okay, so when r is 20 and dr/dt is -3, okay, so just crunch the numbers. 20 squared is 400, times 4 is 1600, times 4, and then I need to do times 3, so which is minus 4800, right? Yeah. And then, of course, we've got our pi there for good measure. What are the units here? Well, what should they be? Cubed per second, because this is a rate, right? This is how fast is the volume changing. Well, what units are volume measured in? here cubic centimeters, right? Okay, and what unit is time measured in here? Oh, I'm sorry. Okay. Let me change that to minutes. That's maybe a little bit more reasonable. 33 centimeters a second is pretty fast. That'd be like if well, if you take your snowball and it's sitting in hell, okay, because then we can, make the joke about a snowball's chance in hell, and right, so or nuclear explosion, or such like. Okay, so okay, yeah, so my bad. But point being though, right? What is volume measured in? Cubic something or others, and what is time measured in? Well, some sort of time unit. Okay. Now that said, actually, what other units can you use for volume? Huh? Yeah, you could also use something like liters or gallons or whatever. Okay, but at least in the case of liters, what is the relationship between liters and uh, say or say a cubic centimeter? Does anybody happen to remember? 1 milliliter is 1 cubic centimeter. Okay. Yeah. So it is actually possible to convert between uh, a sort of volume unit that's not dimensional in the sort of geometric sense, right? Yeah. Okay. So we get whatever number we get, and there we go. Okay. Good. Now, so what other questions could we ask here? Um, well, not a whole lot, because what are the only two variables in question? The V and R. Okay. So we could ask, okay, what is the thing at specific values of t? Okay. Um, but so this is maybe one of the things that's a little hidden here. Let's say that you pick a particular volume, right? Like 100 cubic centimeters. Do I know when this thing is at 100 cubic centimeters? I could determine it, but do I know right off the top of my head? No. Okay. Where could I determine that? Well, what equation do I have that tells me something about the relationship between the volume and something else? Here. Okay. I could tell you what radius I'm at when my volume is whatever, but do I know the time at which that happens? Not quite. I'd have to think harder to figure that out. Okay. So essentially, the takeaway from this is everything depends on T, but you may not have an explicit formula for how it depends on T. Okay. So if we don't have explicit formulas, then we're doing everything kind of implicitly, right? And you can look at related rates as, you remember when we did implicit differentiation? Yeah? All right, now let's throw story problems on top of it, right? Because what are y'all's favorite things in the world? Story problems. Yeah? Yeah? Okay, good. All right, so um, let's maybe start thinking about the next one, and we'll have to come back to finish. Well, actually, no, we'll just start that one at the beginning next time. Um, okay, so the sort of broad stroke steps here. Um, in all of these sorts of things, you need to get what I'm going to call a key equation, okay? And it's some equation that's going to relate all of your variables together, okay? In the snowball problem, it was, not shockingly, the velocity, or sorry, not the velocity, the volume of a sphere, okay? It could be things like the surface area of a sphere, or the area of a circle, or something along those lines. Okay. Another very common one is going to be Pythagoras' theorem. Okay. And in fact, the next example we'll look at our key equation will be Pythagoras' theorem. Well, we've got some sort of triangle action going on. Okay. And then there'll be a few other more esoteric ones that we'll talk about. Like we could deal with the volume of a cone. That one's fun. And so on. Okay. But you want to first figure out what is your key equation. Okay. And then you want to figure out, do you know values for any of the variables? Some of them yes, some of them no. Okay. And then you want to take the derivative of your key equation, and you do that implicitly. Then you start plugging in values to solve for the missing components. Okay. But again, don't plug in too early, because if you do, you'll end up with a bunch of zeros everywhere, and that's not really all that interesting. Okay. Most of the time, okay, because it, like, for example, let's say, for example, the problem we worked a minute ago where we were throwing the rock up in the air, like 0 was relevant, right? There was an instant in time when the velocity was 0, okay? And so maybe, just maybe, you've stumbled on that interesting point in time, okay? But most of the time, the numbers are not going to be 0 for the related rate stuff, okay? So if you do get 0, that should set off your bullshit alarm that, hey, maybe there's some bullshit, and just double check. Okay. Okay. So last piece of business, the video problem that seemed to go okay for those of you who have done it. Okay. So get her done if you have not. And then on Monday we'll do the next set of, the next exam. So what's the story there? Go get it out of the folder. Go find a quiet place to work. Return it to the folder. You work everything on separate paper, and also staple it. And also, if you use notebook paper that you get out of a 3-ring thing, you remove the frillies, right? Okay? All right. I will see you guys on Monday.